All right, I'm going to go over some notes for the 13 toolkit functions. And they're called toolkits because they're functions that we need to, when we think about the equation y equals x or absolute value of x, they're functions that we need to have a picture of them in our mind when someone says those words. The graph of y equals x looks like, and we have to have that bing goes in your brain, and you know what it looks like. So if you have to do index cards or something to help you memorize what they look like and what their properties are, then I would do that after the video. Okay. These are the guided notes that I provide in class. So if you would please print them out and spend a couple of minutes. You know, graphing the 13 toolkit functions, except with the exception of the greatest integer function, which we'll talk about in this video. But this one you may not know how to graph on your calculator or on Desmos, but I'll show you how to do that. Okay? All right, so just take a second, pause, and then just all I want you to do is graph these and then answer as many of these questions as you can about domain and range and symmetry, etc. And then we'll come back to the video, and then we will I'll show you how I filled it out. All right? So we'll see you in just a second. All right. So let's get started talking about toolkit functions. All right, and here are my graphs, and let's talk about all of their different properties. Okay, y equals x is a line with a slope of 1, and it's also known as the identity function because x and y have the same identity, y equals x. All right, the domain for this function is all real numbers. The range is also all real numbers. This function is continuous. From the second I put my pencil on the page and draw it, the function is continuous. So that is also for all real numbers, it's continuous. The symmetry. Now the proof for symmetry is if you plug a negative x in. Let's do that down here. F of negative x equals, I'm going to put negative x in my function, and I get negative x. And then I get negative x, which happens to be equal to negative f of x. So we know that our function is then odd because it has the property of f of negative x equals negative f of x, or the opposite of it. Okay, it's symmetric with respect to the origin, which makes it odd visually. Okay, so we will write odd here. All right, the extrema, this function has no absolute max, min, or even relative extrema, so this would be none. And it's increasing for all real numbers, and it doesn't have any decreasing intervals, so but not applicable. Now, boundedness. Boundedness means are the y's bounded by any y value, y values, and the y equals x is certainly not bounded in the in the y direction because it goes off to infinity and negative infinity. So this is not bounded. The limit as x goes to infinity, if I were to go and take x and make it go to infinity, the y, or f of x, is approaching positive infinity, so that goes to infinity. The limit as x goes to negative infinity. As x goes to negative infinity, the y is headed towards negative infinity. Those are the end behavior limits. All right, the absolute value function. The absolute value function looks like the classic V. It has a slope on the right of 1, a slope to the left of negative 1. Its domain is all real numbers. Its range, I only have y values starting from x inclusive of 0, or I'm sorry, y inclusive from 0 to infinity. Is this continuous? Yes, it's continuous for all real numbers. Its symmetry, let's do the proof for symmetry. If I were to plug in f of negative x into the absolute value function, I would get f of absolute value of x, which is equal to f of x. So f of negative x is equal to f of x, which means this function is even. All right, so we're going to put even up here. And it's symmetric with respect to the y-axis, which also visually shows you that it's even. The extrema, well, this function has a low point, and it's an absolute extrema, so we would say absolute min of 0 at x equals 0. And the increasing intervals If I were to put my finger on the function moving from left to right, my y's are decreasing, and the x intervals where that happens is decreasing, negative infinity to 0, and it's increasing from 0 to infinity. Now just remember, please, that increasing and decreasing behavior is in terms of you state the x intervals where the function is increasing or decreasing, because when you say a function is decreasing, you're already talking about the y values, right? The y values are decreasing. For what intervals? Well, from when x is negative infinity to 0, my function is just decreasing. And then from 0 to infinity, my function is increasing. The boundedness. Now, this function is not bounded from above, excuse me, because I have y values that want to go to infinity. But it's bounded below, because there is a bound below for which the y doesn't go below, right? So it's bounded from below because I have a low y value of 0, and there's nothing else below that. All right, the end behavior limits. The limit as x goes to positive infinity, f of x is headed towards infinity. As x goes to negative infinity, my f of x is headed, or my y's are headed to positive infinity. And even functions will have the same end behavior, all right? All right, moving right along. Y equals absolute, or x squared. This is our classic quadratic. The domain on this is all real numbers. The range is inclusive of 0 from 0 to infinity. This is also continuous for all real numbers. The symmetry is even, but let's prove it. We'll say f of negative x equals negative x quantity squared. And when you square a number, negative x times negative x is equal to positive x. So this is positive x squared, which is f of x. So we have found our original function, which means this is even. And you can see it from the graph. It's reflected over the y-axis. So this is even symmetry. And does it have extrema? Sure, it has an absolute extrema. So we would say an absolute min of 0 at x equals 0. The increasing intervals are y is increasing when x is going from 0 to infinity. Y is decreasing when x is negative infinity to 0. Boundedness. This, like the absolute value function, is bounded below. The limit as x goes to positive infinity, if I take my x's and I go to positive infinity, the y's, or f of x, is headed towards infinity. The limit as x goes to negative infinity is going to be the y's are going to positive infinity. All right, that's the square function. Now this is the cubed function. The domain on this one is all real numbers. The range is all real numbers. This function is obviously continuous for all real numbers. It's symmetry. Let's do the proof for symmetry. That would be f of negative x equals negative x quantity cubed. And if I cube, excuse me, a negative number, excuse me, if I cube a negative number, I get negative x times negative x times negative x, which gives me negative x cubed, which is equal to negative f of x. So f of negative x equals negative f of x, which means I have an odd function. And you can see from the graph, I hope, that it's symmetric with respect to the origin, and it is definitely odd, just like it's y equals x cousin from up here. All right, this function has no extrema, so I'm going to put none here because it's increasing. The increasing intervals are all real numbers because it's increasing from negative infinity to infinity. The decreasing intervals, well, this doesn't apply. The boundedness, are the y's bounded in any way? Meaning, are the y's restricted? No, they aren't. So this is not bounded. The limit as x goes to infinity, that's if x gets bigger and bigger and it goes to infinity, the f of x or the y's are going to infinity. The limit as x goes to negative infinity, the y's or the f of x is headed to negative infinity. All right, so we've gone down 4 already. The identity, the y equals x, absolute value of x squared, and x cubed. So hopefully nothing new yet. Let's move on to the square root function. This is a square root function, classic. Its domain is 0 to infinity inclusive. The range is the same, 0 to infinity. Is this function continuous? It is. From the second I put my pencil on the page and I draw it, I don't have to pick it up. So this is definitely continuous from 0 to infinity for when it exists. The symmetry, well, clearly this is not symmetric with respect to the origin or the y-axis, so there is none. The extrema, well, we have an absolute low spot here, so this is an absolute min of 0 at x equals 0. The increasing intervals, well, it's increasing for from 0 to infinity, and it's not decreasing ever, so this is not applicable. Boundedness, well, is there a y value that's restricting or bounding the y's? Well, not on this side, not as you go up, but down here you have a lower bound, so this is bounded from below. Bounded below. And let's talk about the end behavior limits. Well, the limit as x goes to infinity, f of x or y is headed towards infinity. The limit as x goes to negative infinity. Now, if I were to travel down this x-axis all the way to negative infinity, and I were to look up and down, is my function even existing over here? The answer is no. So this would mean that the limit doesn't exist because my function doesn't exist there. Okay, so that's the square root function. All right, what about f of x equals 1 over x? This is a name, this is the reciprocal. That's what this one's called. And obviously this is square root, and the other one was square and cube. But this is kind of a unique name. So it's the reciprocal function. Why do they call it that? Well, because it's 1 over x, which is the reciprocal of y equals x. All right, so if you look at this graph, some interesting things are going on. The domain is going to be negative infinity to 0, exclusive, union 0 to infinity, because I can't have a 0 in the denominator here. And when x is 0, I have a domain problem. The range, all the possible values for y are negative infinity, and then I have to hop over y equals 0 to see the rest of my graph. So it has the same range. All right, now, continuous? Well, no, this is not continuous for all real numbers. It's continuous everywhere except x equals 0. What kind of discontinuity do we have? We have an infinite discontinuity. Okay. And why is it infinite? Because when I approach 0, my function is headed to negative infinity or infinity. Extrema, does it look like it has any high or low points? Well, the answer is no, so it's none. Oop, I skipped over symmetry. Let's practice symmetry. So f of negative x equals 1 over negative x, right? And I can bring the negative out in front. And I get f of x equals negative 1 over x, but that's just negative f of x. And I think you can see from the picture that it's odd. It's reflected over the origin, and they're in opposite quadrants there. So symmetry is odd. Increasing intervals. So let's put our finger on the function. What's happening? Well, it's going down, going down. So it's always decreasing. So there are no increasing intervals. And the decreasing intervals are negative infinity to 0, exclusive, in union with 0 to infinity. Does it have a horizontal asymptote? It surely does at y equals 0. It has a vertical asymptote at x equals 0. Are the y values bounded? No, because it goes to infinity up here and infinity, negative infinity down here, so it's not bounded. And the end behavior limits are as x goes to positive infinity, the y or f of x is approaching 0. As x goes to negative infinity, the y, or f of x, is headed towards 0. All right, so that is the reciprocal function. Next one is the cube root function. The cube root function looks like this, almost like the square root in this quadrant, and then it's got a piece over here because you can take the cube root of negative numbers, and that's why it's got domain on both sides. So the domain here is negative infinity to infinity. The range is also negative infinity to infinity, and it's continuous for all real numbers, negative infinity to infinity. The symmetry, let's prove it. We have f of x equals the cube root of negative x. And you can bust this up into the cube root of negative 1 times x. And the cube root of negative 1 is negative 1, so I can bring that out, and this is the cube root of x, which is equal to negative f of x. So we have f of negative x. Oops, I should put a negative x up here, I'm sorry. F of negative x equals negative f of x, so we know that this is odd. And if you look at the picture, it does look symmetric with the origin. So this one is odd. The extrema, well, this has no extrema. This is also increasing for all values of x and never decreasing. So that's not applicable. The boundedness, are the y's bounded? No, well, it's going to go to infinity, but it's going to get there very slowly. So this is not bounded in either direction. The end behavior limits, as x goes to infinity, the y or the f of x is headed to infinity. You should go to negative infinity. X goes to negative infinity. The y or the f of x is headed to negative infinity. And that's the cube root function. Next we have the exponential e to the x. E to the x, its domain is all real numbers. Its range, as you can see, you have a horizontal asymptote here at y equals 0, is open or exclusive of 0 to infinity. It is continuous for all real numbers. It has no symmetry. I'm going to put none. It has no extrema. It is only increasing from negative infinity to infinity. My finger on the function is always increasing. Decreasing intervals, none. They're not applicable. Horizontal asymptote at y equals 0. Boundedness, okay, well, it's not bounded from above, but it does have a lower bound, so it's bounded from below. Bounded below. The end behavior limits. As x goes to infinity, y or f of x is going towards infinity, positive infinity. As x goes to negative infinity, the y or f of x is approaching 0. All right, that's the exponential function. All right, moving along. Natural log of x. This happens to be the inverse of y equals e to the x. Now, e to the x had a point, if we were to look at it over here. I'll put it next to it. Do you see how, if I were to graph the line y equals x, that this curve is a reflection over the line y equals x. That they're reflections of each other. So they're inverses for sure. And when you have an inverse, the y equals 0 asymptote here for the e to the x becomes x equals, because when you do inverses, you switch the x and the y. So this becomes a vertical asymptote. And this point here, 0, 1, becomes 1, 0, because you switch the x and the y when you do inverses, okay? All right, the domain is 0 to infinity. The range is all real numbers. The y's can be anything. It's continuous from 0 to infinity. It has no symmetry. It has no extrema. And by the time, when you put your finger on the page, it's always increasing. So it's increasing from 0 to infinity. And it's never decreasing, so we're going to put not applicable. It has a vertical asymptote at x equals 0. And are the y's bounded? Nope. So this one is not bounded. The end behavior limits as x goes to infinity. F of x or y is headed towards infinity. The limit as x goes to negative infinity. Well, if we were to head all the way out here, is the y anywhere to be found? Well, over here, this function doesn't even exist. So this would be does not exist, okay? Because the log function doesn't exist at x equals negative infinity. Now, there is a limit as x approaches 0 from the positive side. That means as x gets closer and closer to 0 from the positive side, what is your f of x getting closer to? Or your y is getting closer to what? Negative infinity. Similarly, the limit as x goes to 0 from the left side of f of x. Do I even have a function on the left side of 0? No, it's like my function doesn't exist over here. So therefore, the limit doesn't exist. So that's a DNE. All right, greatest integer function. This is also known as the floor function. Okay, now what is it meant to be a floor function? Well, I'm going to take my piece of paper here and we're going to talk about, I'm going to zoom in with my paper, if that's okay. Zooming in, really zoomed in here. So this is going to be 0, and this is an open dot. 0, I have a closed dot and then open, closed dot, and then open, and open, closed, open, closed. It's like a set of stairs. And these are all integer numbers, which are nice numbers. Most students love integer numbers. Now, I'm going to suggest to you that this interval, this is -1, and this is -2, and this is -1, and this is -2, and then 1, and then 2 here. I'm going to suggest to you that this x interval here is -2 to -1, and I'm going to leave that open. All right? That makes sense, doesn't it? This x interval is going to be what? -1 to 0, and that's open. This interval is going to be what? 0 to 1, and it's open on the right end. And this one's going to be 1, 2, open. And then we're going to have an interval that is 2, 3, open. And of course, it keeps going on forever, okay? And if I were to turn this over, this is like the floor of my house, and I have a curved roof, right? And this is the ceiling. This would be the floor, ceiling, floor, ceiling, floor, ceiling, floor, ceiling. Okay? Now they call this the floor function because if I were to plug a number in, let's do an example. Let's say we want to know f of x is equal to the integer or int x, okay? Let's say I want to plug in 1.5. I'm going to plug in 1.5. Well, if you go on the graph here and you go to 1.5 and you go up to see what your y value is, it's 1. Well, what integer interval is 1.5 in? Well, 1.5 is in this integer interval, 1 to 2. And this function, its output will always be the floor of the interval. So this would be 1, because this interval between 1 and 2, its floor is 1, right? Remember, this is floor, ceiling, floor, ceiling. If I wanted to have f of -0.7, what integer interval is -0.7 in? If I plug -0.7 in for x, it's going to be right here. And that's in this integer interval, and its answer would be -1 because that's the floor of that interval. Okay, that's how the function works. So that's pretty fascinating. And what people like about it when they're studying it is it's a step function. It's a piecewise. It's an infinite piecewise, and it's got infinitely many jump discontinuities because it goes on forever. So I drew a representation of the floor function right here. Now its domain, believe it or not, even with all those discontinuities, is negative infinity to infinity, right? Because everywhere I have a solid dot covered. Its range are all the possible y values that this function has. Well, I have y values at -6, -5, -4, -3, -2, -1, 0. I have all of them, but they seem to be integers. Remember, this means the integer set. Its outputs are only integers. So you can use the fancy z instead of the fancy r for real numbers. All right? Well, clearly this function is not continuous. It's got some areas where it's continuous, so we would say it has jump, discontinuities, I'm going to say discontinuities, IES, at x equals the integer, right? Because every integer, it has a jump discontinuity. It is not symmetric. And we're not going to talk about extrema, increasing, decreasing intervals. I have some intervals where they're constant, okay? The y values aren't bounded, so this is not bounded. Okay, its end behavior limits. As x goes to infinity, the y's are headed towards infinity. And as x goes to negative infinity, this is negative infinity, okay? This talking about extremas and increasing, decreasing intervals, it's complicated, and it's not something that we're going to go into. What makes this function interesting, again, as I stated, is that it's known as the floor function. Its outputs are always whatever the floor is of the integer interval you're in, okay? And it has infinitely many jumps, which is pretty cool, okay? Now, how do we graph it on our calculator? Let's do that really quickly. Sorry, I should have had this open and ready to go. Here I've got my calculator, and I'm going to go to y equals. I'm going to clear this out. And you're going to go to the math menu, and the greatest integer function is under the num, and then you'll see that it's number 5 here. And then I'm going to put x. So that's the greatest integer function int x. Press enter, and now I'm going to go zoom 6 so we can see a standard viewing window. And you'll see that it mirrors this. But what's interesting about this on the calculator is you can't tell whether it's open or closed at each end. So our brains as humans are going to have to be able to know that since it's the floor function, that the solid dot is on the left side of the integer interval, okay? So how do we get there again? Let's refresh our memory. I'm going to go to y equals, clear this out, and it's going to be math. You hit num, and it's number 5. And you put the x and close parentheses and press enter, and you can graph it. And there it is, okay? Very nice. Now, on Desmos, if you were to graph it on Desmos, I already have it here, you would type in y equals the floor function, and you just spell out floor. You know, and believe it or not, I know this is going to sound crazy, there is a ceiling function. A ceiling, which means you would choose the ceiling of an interval instead of the floor. So what is this? This is just a translation or transformation of the floor function, which is kind of cool. But we're not going to talk about that. We're just going to talk about the floor or the greatest integer function. Okay? And what do we find interesting about it? It's got infinitely many jumps. All right, quickly, I'm going to go over sine, cosine, and tangent because we've already done those before recently. The sine function, you know, has a midline of 0, has a whole bunch of stuff going on, but I only drew one period of it. Its domain, believe it or not, is all real numbers. And its range goes from -1 to 1. I adjusted the x values on the x-axis there to make it easier to draw. The range is bracket -1 to 1. It is continuous for all real numbers. It has odd symmetry. And if you go f of -x equals sine of -x, sine has that property where you can pull the negative out, right? And this is negative f of x. So f of -x is equal to negative f of x, which makes it odd. It's extrema. Well, it has an absolute max, but it happens every 2 pi, right? If you can envision yourself drawing the whole function. So the extrema is going to be absolute, I'm writing it small here, absolute max of 1 at x equals pi over 2, because that's where the sine has its max, plus 2 pi n, an element of the integer set, because every 2 pi after that, you're going to hit the 1. It has an absolute min of -1 at x equals 3 pi over 2 plus 2 pi n, and an element of the integer set. The increasing intervals, okay, well, it's increasing from, if I were to keep going here, I'm going to choose one interval, which is this negative pi over 2 to pi over 2 interval. I'm going to put the increasing interval over here, if that's all right, just to have more space. All right, that's going to be increasing from, well, what's the first one? This is at negative pi over 2. So from negative pi over 2 plus, when do I get to the next increasing interval? Well, that's over here, from here to here. And how far away is that? Negative pi over 2 to 3 pi over 2 is 2 pi apart. So this is 2 pi n, and an element of the integer set, comma, and then I end being increasing at pi over 2 plus 2 pi n, and an element of the integer set. And then the decreasing intervals are going to be, I'll choose this one here, from here to here, I'm decreasing. If you follow that, I'm going to make them a different color real quick. This here is decreasing, pink. All right, what is the beginning of that decreasing interval? Well, that's pi over 2. Plus, we're going to add 2 pi to get to the next decreasing interval. And then pi over 2, and then I'm going to end at 3 pi over 2. 3 pi over 2 plus 2 pi n, and an element of the integer set. That's when I'm going to get to the next decreasing part. All right, does it have any vertical asymptotes? No. Is it bounded? So are the y's bounded? They sure are. This one's bounded from above and below. So this one's just flat out bounded. The limit as x goes to infinity does not exist because this function oscillates infinitely between 1 and -1, and it does not zoom in on a single number. And the same thing with this end behavior on the left. All right, cosine x. Cosine x starts off the midline and goes through its period there. Its domain is all real numbers. Its range is -1 to 1. It is continuous from negative infinity to infinity. It has even symmetry. And let's prove it. F of -x equals cosine of -x equals cosine of x if we use the properties that we learned in trig. So f of -x equals f of x, which makes this function even. And it's symmetric with respect to the y-axis. This has extrema. All right, let's do I'm going to do the extrema over here. That's it has a maximum here starting at 0 and then 2 pi away. So it's going to be absolute max of 1 at, it helps if I put 1, x equals pi over 0 plus 2 pi n. So if it's 0 plus 2 pi n, I can just say 2 pi n and an element of the integer set. And it has an absolute min of -1 at x equals, well, the minimum is at pi and every 2 pi after that. So pi plus 2 pi n and an element of the integer set. All right. Now, increasing intervals. Increasing. It's increasing from, we can go from pi to 2 pi. Let's see how that's increasing from left to right. So we can say the lower part of that interval is going to be at x equals pi. So this is going to be pi plus 2 pi n and an element of the integer set. 2, I stop increasing at 2 pi. 2 pi plus 2 pi n, and an element of the integer set. Okay, decreasing intervals, here we go. I need to adjust my worksheets here. Okay, decreasing from 0 to pi. So we're going to put 0 plus 2 pi n and an element of the integer set. You don't have to show the 0. And then it's the end of the interval is pi. So this is pi plus 2 pi n and an element of the integer set. Boundedness, like its friend sine next to it, the y's are definitely bounded. So this is bounded from above and below, so from both directions. It also has no end behavior limits because it infinitely oscillates between -1 and 1 and doesn't zoom in on a specific number. All right, moving right along, tangent. Tangent has a domain problem, and sometimes we can write this as reals not equal to pi over 2 plus the period, which is pi n and an element of the integer set. Or you can write it in interval notation, and I'll start from negative pi over 2 plus pi n and an element of the integer set to, when do we hit the next asymptote? Well, that happens at pi over 2 plus pi n and an element of the integer set. So you can write an interval notation or write it reals not equal to. The range, lucky for us, is all real numbers. Is it continuous? No, we have infinite discontinuities. At x equals pi over 2 plus pi n and an element of the integer set. That's for every asymptote. It is odd symmetry. It has no extrema, and it is increasing for the same intervals as above, so negative pi over 2 plus pi n and an element of the integer set to pi over 2 plus pi n and an element of the integer set, because it's increasing except for its asymptotes. Decreasing, none. The vertical asymptotes occur at x equals pi over 2 plus pi n and an element of the integer set. It is not bounded. The y's are not bounded. And it goes that these do not exist because it doesn't, again, not hone in on a certain number. Okay. Now we're going to name that curve. Sorry, I have a limited amount of time here, so I want to make sure I get through this. We're going to name this toolkit function, and we're going to use a, the stretch factors, as 1 or -1, so we don't have to worry about solving for a. All right, well, this is a parabola that opens up, and the parabolas that open up, I just want you to remember, are f of x equals its stretch factor a times x minus h quantity squared plus k. That's vertex form, where h is the horizontal shift to the right or left, and k is the vertical shift. Okay, so this vertex right here is at 2, 1. So this function is going to be x minus 1 quantity squared. I'm sorry, x minus 2, because that's the shift. X minus 2 plus 1. X minus 2 quantity squared plus 1. And I said the a is 1 or -1, and it's positive 1 because it opens up. This is the square root function, and f of x generically for this one is going to be a root x minus h plus k. Yeah, the yellow is working much better. Okay, so this one is shifted to the right by 3 and down 4. So this one's going to be f of x equals the square root of x minus 3 minus 4, shifted to the right and down. This is the absolute value function. Its generic is f of x equals a times the absolute value of x minus h plus k. This one is shifted to the left by 2 and up 3. So this is going to be negative absolute value because it's upside down. X plus 2 up plus 3. Okay, this one is the e to the x function, or 2 to the x. 1, 2, 3. Actually, yeah, okay. So this is e to the x. So its generic is going to be a e to the x minus h plus k. Okay, the shift down is where the asymptote is, and the shift left or right. What I do is I look at the point 0, 1, which is above the asymptote, and it's not shifted left or right. So this is just e to the x minus 2 because it's shifted down 2. This one here, the asymptote is right here. It's shifted 1, 2, 3 to the left because that's where the 0, 1 went, and it's upside down. So it's negative e to the x plus 3 plus 2 because I shifted it 1, 2, 3, left 3, and up 2. Okay, it's using the same formula except that it's negative. All right, I got to keep moving. All right, now we're going to do some transformations of a function that I'm given, and what it means if I make, this is what the y's are. If this says take all the y's and make them the opposite of what they are, which means I'm going to take the positive ones and make them negative. So here it goes. And then I'm going to take the negative ones and make them positive, right? So it's like my ladle is turned upside down, you know, like if we're soup serving. This says take the sketch and move it to the right by 2. So I'm going to take my sketch and move it to the right by 2, right? I took this point and moved it to the right by 2. This says take all the y values and move them up 2. So this is only down 1. So we're going to go 1, 1, 2. So we're going to go up like this and like this. So we've moved them all up 2. This says we're going to move it left 3 and down 1. So 1, 2, 3. And down 1, sorry. 1, 2, 3, and down 1. So it should look something like that. All right, this one says we're going to reflect it over the y-axis. So it's going to take my ladle and we're going to put this on this side and this on this side. Because we're flipping it across. So we're taking all the x's and we're taking them and making them negative. This one says we're going to take the y values and multiply them by 2. So this negative 1 is going to become negative 2. So it's going to make it taller and the slope steeper. So it's stretching my ladle out. All right, now I'm going to do a table, okay? So I'm giving you a bunch of x values and a bunch of y values, and we're going to figure out what this table wants us to do. It says take all the y values here, all the f of x values, and multiply by negative 1. When I do that, I get 4, 1, negative 2, negative 3, 0, 3, and 6. All I did was take the f of x's and make them negative. This says take all the f of x's and subtract 2. So this negative 4 minus 2 is negative 6. Negative 1 minus 2 is negative 3. 2 minus 2 is 0. 3 minus 2 is 1. 0 minus 2 is negative 2. Negative 3 minus 2 is negative 5. Negative 6 minus 2 is negative 8. This says we're going to add 2 to all the y values. So negative 4 plus 2 is negative 2. Negative 1 plus 2 is 1. 2 plus 2 is 4. 3 plus 2 is 5. 0 plus 2 is 2. Negative 3 plus 2 is negative 1. Negative 6 plus 2 is negative 4. This says we're going to take the x's and make them negative. So I'm going to say x is negative 3, but when I plug a negative 3 in here, I get f of negative 3, which means I'm going to put f of, where's f of 3? Because when I plug negative 3, I get a positive 3 in. So I want f of 3. F of 3 is negative 6. Then I plug negative 2. Negative of a negative 2 is 2. So I'm going to f of 2, which is negative 3. Plug in negative 1. F of a negative 1 is f of 1, which is 0. F of 0 is just 0. I mean, whatever f of 0 is, which is 3, I'm sorry. Right? That's 3. All right. Then f of negative 1 is 2. F of negative 2 is negative 1. And f of negative 3 is negative 4. And so what it's done is taken the values on this side and put them over here, and the values on this side and put them over here for this line, right? It just took the x's and flipped them, reflected them across the 0. This says we're going to take the graph and shift it right by 2. So what happens? I'm going to put negative 3 in here. So f of negative 5. I don't have a negative 5 up here, so that's a blank. F of negative 2 minus 2 is negative 4. I don't have a negative 4, so that's a blank. F of negative 1. When I put negative 1 here, I get f of negative 3, which is negative 4, which is my shift. So now I know I can plug in negative 2, and I get negative 2 minus 2 is negative, I'm sorry, f of 0. F of 0 minus 2 is f of negative 2, which is negative 1. So it's confirming my shift to the right. So I'm going to take all these values and shift them to the right. And then I don't put them over here because I ran out of space, right? This says take all of the f values, the f of x's, and multiply them by 2. That's going to be negative 8, negative 2, 4, 6, 0, negative 6, and negative 12. This says we're going to move it to the left. So let's plug in negative 3. When I plug in negative 3, I get f of negative 3 plus 2, which is f of negative 1, which is 2. And then I plug in negative 2. That's f of 0, so I put 3. Plug in negative 1. I get f of negative 1 plus 2, which is f of 1, which is 0. And so what I've done is, you can see I've shifted them. So let's plug in 0. I get f of 2, which is negative 3. Wait, did I do that right? Let's try again. F of negative 3 is negative 1, which is 2. F of negative 2 minus 2 is f of 0, which is 3. Yes, okay. F of negative 1 is f of 1, which is 0. And then f of 0, I'm sorry, is 2. F of 2 is negative 3. I'm sorry, I got lost. F of 1 plus 2 is f of 3, which is negative 6. And we shifted the graph to the left. Now, we took these values and we shifted them to the left by 2. All right, now this says to take the negative values of f of x and divide by 3. So I'm taking this row and I'm going to divide everything by 3. So that's going to be it's going to be 4 thirds, 1 third, negative 2 thirds, negative 3 over 3, which is negative 1, 0, 3 over 3, which is 1, and then 6 over 3, which is 2. You see, this one here, this row here, I already had the negative f of x done, and all I had to do was divide each one of these numbers by 3. Okay, really quickly before the bell rings today, I want to do this one really quickly because I think I lost everybody, including myself. So when I plug negative 3 in for x, I get f of negative 3 plus 2. Negative 3 plus 2 is negative 1. So I go to the negative 1 column and I pick up the y value here and I put it here, which is 2. F of negative 2 plus 2 is f of 0. I go to this f of 0 column and get the 3. Okay, then I plug in 0. F of 0 plus 2 is f of 2. So I'm going to go to 2 and pick up, so I try again. I plugged in negative 2, I got f of 0, which is 3. Okay, now I'm going to plug in negative 1. Negative 1 plus 2 is 1. I go to the f of the 1 column and put a 0. And then I go to 0. 0 plus 2 is 2. And then I put in the negative 3. Okay, so just double check yourself on this one. If you have any questions, come see me about it. And I'm sorry I was rushing, but the bell here, 4th block, is about to ring. And I wanted to make sure I had this video done for folks to have it in preparation for their test, okay? You guys have a great day, and I will chat with you later. Thanks.